So far, you guys have looked at objects moving at constant velocity. The position time graph looked like this. As time passed, the position changed in a linear fashion, which meant as each instant went by, you went the same distance. It's time to move on to more interesting motion. We haven't talked at all about what causes constant velocity or what we could do to change an object's velocity, and that's what I'd like to go into next. To start this discussion, I'd like you to look at one more constant velocity motion, a car coasting down a table. What I've got here is a motion detector. And a motion detector, it actually works the same way a bat, the little furry flying mammal, goes hunting. A bat uses something called echolocation, which means it sends out a click of sound. That sound goes off, it bounces off its target, it bounces back. And the bat's brain can actually process the difference in time between when it clicked and when it heard its click. And that lets it make a map of where bugs are and things like that. So this thing does something similar. There's a sensor here that makes a click, and it sends the clicks out, and it's going to reflect off this stack of textbooks I got here. And those clicks are going to bounce back and be detected by the computer. So I'm just going to go over here to start. Give it a push. And now stop. So we have this graph here. Since this is a position time graph, we can see that there's horizontal, slope of 0. That's when the cart was not moving. We then have a positive slope that's relatively constant. It was going in this direction. And then, after I stopped it, back to a slope of 0. That's when it was stopped down there. The reason I wanted you to see that particular motion was, unlike our other constant velocity motions, there was nothing keeping that cart going. In the other labs, we had someone walking and their muscles were pushing, or there was a motorized vehicle. But here it just coasted. And you saw from the graph that was plotted on the screen, it appeared to be constant velocity. It appeared to be a straight line. Now we know that that wouldn't have gone on forever. We know it would have slowed down. But a guy named Galileo Galilei in the 1500s, he realized that the only reason it would slow down was because there was something messing with that cart. There was something pushing on it. And pushes or pulls are the next topic we're going to have to discover if we want to understand how motion changes. Galileo began to formulate what we now call Newton's first law. Objects in motion stay in motion unless acted on by a force. Objects at rest stay at rest unless acted on by a force. There's a certain parallelness to those two statements. So you can kind of combine these two and say objects keep doing what they're doing unless you force them to do otherwise. This video is to discuss how Newton's first law was discovered. And the strange thing is, although we call it Newton's first law, the research was done by Galileo nearly 100 years earlier. And what Galileo was interested in was how objects roll up ramps. So he had an experimental setup, kind of like I have here. I have a ramp. I'm going to drop these two brass cylinders down it. They're going to roll up these two other ramps. And one of them is short and steep. The other one is long and shallow. The reason Galileo was looking at different ramps was by changing the steepness, he was actually changing how much of the force of gravity was acting on the motion. The more horizontal, back, forth the motion is, the less the force of gravity is going to have an effect on it. Because gravity is an up-down vertical force. So by making the ramp short and steep, you had more of the gravity force acting. By making it long and shallow, it's kind of like you diluted gravity.
Galileo in the 1500s didn't have the ability to go to space or anything, so this was the only way he could really increase or decrease the effect of gravity. So what we'll do, you'll see this from a couple different angles. You'll see these two cylinders roll up, one from the perspective you have now, and once from a camera that's over here. And then after this whole video is over, you'll see a screenshot from Tracker, so you can see precisely where the two stopped. So let's do the experiment. So I plugged that video into Tracker, and you could see the results. Regardless of whether you were on the steep ramp or the shallow ramp, the tracks end at the same height. The two cylinders went to the same height. And what this implies is that the horizontal motion of the cylinder on the longer ramp was totally irrelevant. Gravity and up-down force stopped them both the same, and the left-right motion wasn't affected by it. So we know gravity is what's causing it to slow down and stop, and that's happening at the same height for both cylinders. But what's making this one go farther? What's making its horizontal motion happen? Interestingly enough, Galileo says nothing is. It's simply that it started with that horizontal motion. So Galileo was doing this experiment. He noticed that the shallower he made the ramp, the less the force of gravity. The thing rolled longer and longer and longer. And he basically started to think about, what would happen if I made it flat, horizontal? Well, the cylinder doesn't stop till it gets to the appropriate height. But if it was totally horizontal, it would never get to that height. And Galileo had the insight, oh, it should roll forever. And that's what gave him the idea that objects in motion stay in motion unless they're acted on by an outside force. If gravity wasn't there to slow it down, it should just keep going forever. Now, we don't see that in the real world because the frictional forces are actually fairly substantial. It does stop after a while. But that was the insight, that in an ideal world, the thing would never stop if it was rolling horizontally. And that's what gave us what we call Newton's first law.
So Newton's first law, objects in motion stay in motion unless acted on by a force. Objects at rest stay at rest unless acted on by